Okay, hi everyone. So this is a tutorial session, the last tutorial session for the course. This is a tutorial session for fuzzy logic and fuzzy system. Sorry, I feel a bit cold, so I apologize if I cough. So Daniel, our TA, kindly recorded a tutorial session on fuzzy logic and fuzzy systems, but that didn't completely match what I had in mind. As a result, we decided that I make a tutorial session on behalf of the TAs and me. So hopefully it will be useful, and please study this session as well as other lectures for the exam. So study all lectures and and the tutorial sessions for the exam, please. And so let's go and see what we. So first, quickly, let's see what we saw in a fuzzy logic and fuzzy system. So for fuzzy sets and fuzzy logic, we went through the fuzzy sets in contrast to crisp sets. And then we said that we have a membership function, we had the symbolic representation, and then we talked about the membership functions in the lectures, right? Then we talked about important membership functions. Then some main fuzzy logic operators, which are T norm, S norm, and complement. And so we introduced these things and some examples. Then we talked about several other operations on single fuzzy sets, including height or modal grade, support set, alpha cut, measures of fuzziness, set dilation, and contraction. For set dilation and contraction, we had an interesting example for age. And we said that we can have different combinations of approximate reasoning using these operators. For example, we assume we have membership functions for young and old, then we can make more or less old, not young and not old, too young, young but not too young, something like that. And that's interesting. Then Then we talked about operations for relational fuzzy sets, such as set inclusion, set equality, implication, extension principle, projection, and cylindrical extension. We talked about all of these. So this is what we had. Then we went into, then we went and talked about the fuzzy inference systems. And then we said a fuzzy inference system gets crisp signal as input and outputs a crisp output, so it has three parts: fuzzification, fuzzy rules or reasoning, and defuzzification. Fuzzification is required to convert crisp signals to fuzzy signals, and defuzzification is required for doing the other way around, to convert fuzzy output to fuzzy signal to crisp signal. And then we also have fuzzy rules or reasoning in the middle. So for fuzzification, we talked about several possible methods, such as singleton method, triangular function method, Gaussian function method. Then for defuzzification, we talked about several methods, such as centroid method, mean of maximum method. Sorry. Smallest of maximum, largest of maximum, bisector of area, and threshold method. For fuzzy reasoning, we first compared fuzzy function with the crisp function. Then we talked about Max-min composition. And then we derived how to handle rules. First, we started with simple cases, then we made it harder and harder. So first, we started with single rule and with single antecedent and single input. So single input, single output, and one rule. Then we made it a bit harder. We made it a single rule, but multiple inputs. So that was a typo, so I changed that antecedents to inputs. So now I have one rule, but I have several inputs. Then we made it harder and said, what if we have multiple rules and multiple inputs? So it's kind of a general case then. And we showed how it is working. And then we said that we have at least 3 very important fuzzy inference systems. One of them is Mamdani. What we talked about so far was Mamdani, proposed in 1974, which uses max-min composition. It uses a mean operator for T-norm, max operator for S-norm, and it uses max-min composition as well. Then we said we can also have input-output curve. This input-output curve is not just for Mamdani. It can be used for any fuzzy inference system. And assuming that we can sweep over all possible, over the whole domain of input, then with fine steps, then we can have this input-output curve calculated and then throw away the fuzzy inference system later. Although this curve has been obtained by the fuzzy inference system. But usually in higher dimensions, it's not feasible to cover the whole domain of inputs. And then Sugeno fuzzy system, or Sugeno. Sugeno or Sugeno, I don't know how it's pronounced. I think it's Sugeno. Sugeno fuzzy inference system, we introduced that. And then it was proposed in 1985. It's also called Takagi Sugeno Kang fuzzy system. So what does it do? So this part is the same as Mamdani fuzzy system. So it has fuzzification. It has everything as before. It calculates the W1, the firing strengths. But for output, it uses crisp functions where the X or the input, XY here, are crisp, not fuzzy. So these are crisp inputs. And the Z's are also outputs of the functions are also crisp. So the whole function is crisp. Its input is crisp, output is crisp. And but where is the fuzzy used here? So here, the W's. We use the W's or the firing strengths for weighting these outputs, and we calculate the average, the weighted average of them to have the total output, the overall output. Then we also said that we have Tsukamoto fuzzy system. What does it do? So again, this part is the same as Mamdani. We find the firing strengths, but for output, Mamdani could use any membership function, but here we in Tsukamoto fuzzy system, with the output membership functions need to be monotonic, either increasing or decreasing. Why? Because we need to get the inverse of the membership function. For that, we need to be monotonic. Otherwise, for one membership value, we might have several input values, right? And these inverse of membership function is crisp itself. Then we get calculate the weighted average of the crisp outputs. What are the weights? The firing strengths, W1, W2. Then we talked about advanced topics in fuzzy logic, such as type 2, complex fuzzy logic, quaternion fuzzy logic, and fuzzy system in MATLAB and Python. And we talked about different things here, and these are the references. So this was what we talked. Now let's go into some examples. For fuzzy sets and fuzzy logic, I think it's straightforward. I have also provided various examples. So please study that, and I think there is no need to give more examples in the tutorial for this slide deck, because I think it has already enough examples, and I think it's a straightforward. For fuzzy system, we need to become a bit more detailed because there are some things that there was no time for me to go over in the main lecture, and I'm gonna cover that in the tutorial. And that this part is also important for exam. So let me tell you briefly about the fuzzy system again. Consider Mamdani. Do you remember I told you in the previous lecture, where was that? Here. I said, so here, if you see my cursor, what are these? Mu A prime, mu B prime. These are the fuzzified crisp inputs. So we have some crisp inputs, A prime, B prime, or XY, whatever we call it. And then we fuzzify them. So the crisp values become some membership functions, right? And then what is this part? So whatever I'm circling here is already in the fuzzy inference system, right? So here these are the mu A1, mu B1, mu A2, mu B2. These are already in the rules, right? And also the membership functions of the outputs are already determined in the system. Then then the fuzzified signal fuzzy output signal is this, right? Then we need to defuzzify it, right? So this goes into defuzzification, which gives us a crisp Z, right? So that's the whole thing. Also, we can have similar discussions for the Sugeno and Tsukamoto fuzzy systems. Now, how do we find these rules? How do we find these rules? This is the part that I didn't have time to cover in the main lecture. So these rules are determined in this way. First, for example, we want to design a fuzzy inference system. We go to experts in that area. Experts, so we want to design the fuzzy inference system for some application, right? Any application it can be. It can be application of washing machine. It can be application of controlling rockets. It can be application of subway, application of whatever you can think of. Any it can be biotechnology application, anything, right? So, or it can be image processing application, different things. Then we go to the experts of that area. Assume we wanna design a fuzzy system for let me think, for a vehicle, right? For controlling a vehicle, and then for self-driving car maybe. And then what do? We go to the experts of vehicles. Then, for example, they tell us some rules. So we see, do you agree that any expert that wants to do something in their own job, they have some rules in their mind, and these rules are crisp. For example, let me tell you some example here. So here, for example, assume we go to the expert of a vehicle, and the expert tells us I have 4 rules. It can be many rules. Here, for example, 4 rules in my mind whenever I want to design something or I want to work with something, right? So, and then we ask them, please let us know your rules, so I write it down. Assume they say, if a slope, so if the vehicle is on the road, right? So the road has some slope. So the rules are if then, and the rules might have several inputs and one output usually, right? So for example, if slope is negative, this is the rule in their mind, in the expert's mind. If a slope is negative and gear is low, then gas should be low. So how much you should push the gas pedal, I mean, gas should be low. So, and the gear can have several values, gear low, high. Yeah. So let me tell you one thing. For the rules, the expert will tell us some rules, and these rules has some inputs and outputs, right? For example, the inputs in these rules, let me read the 4 rules for you first. So if a slope is negative and gear is low, then gas should be low. Okay. Second rule, if a slope is negative and gear is high, then gas should be medium. These are determined by the expert. If a slope is 0, then gas should be medium. If a slope is positive, then gas should be large, right? So you might be wondering, how do we know that the slope can get 3 values, negative, 0, positive? These are again determined by the expert, right? So these are, of course, approximate reasoning, because the expert doesn't say how much negative. The expert only says negative, right? Negative, 0, positive. And so the expert in the rules of expert, for gear, we can have low and high values, right? And for gas, we can have low, medium, large, according to the expert. Also, note that 2 of the rules have only 1 input, and 2 of the rules have 2 inputs. So the number of inputs in the rules might differ. So they don't need to be necessarily the same. They don't need to have the same number of inputs necessarily, right? And okay, so slope negative, 0, positive, gear low, high, gas low, medium, large. Now let's go to the next slide. So for these 3 things, so 2 of them were input and 1 of them was output, right? So slope and gear were input of the different rules, and gas was output. Okay, for both inputs and outputs, we need to determine the membership functions. But how many membership functions per input or per output? It is determined by the rules. For example, the slope can get negative, 0, and positive. So we need 3 membership functions for slope. 1 for negative, 1 for 0, 1 for positive. The gear can have low and high, right? Yes, low and high. So we need to get 2 membership. We need to consider 2 membership functions for gear, low and high. For gas, we need 3 membership functions, low, medium, and large, right? Okay. So now, another question that you might be wondering is that, how do we know the domain or the range of inputs and outputs? For example, a slope here, I'm assuming it's between -10 and 10. Gear, I'm assuming it's between 0 and 5. And gas, I'm assuming it's between 0 and 10, right? How are these determined? Again, according to the application. So if either the expert can tell us or we can figure it out ourselves. For example, slope, we measure different experiments and we see that it's between -10 degrees and until 10 degrees, or 10 radians to 10 radians, whatever we call it. And the dimension of these variables, again, is determined by us, whether it can be degree, it can be radian, etc., right? And for gear, so of course it's between 0 and 5, because we have gear 1, gear 2, gear 3, gear 4, gear 5 in manual gearbox, right? And for gas, again, we can figure it out. Maybe let's have it between 0 and 10. And even if we don't know the domain, maybe in some applications we can normalize that variable to be between 0 and 1, or etc. It is determined by us and the expert together, right? We can normalize it, we can determine the range. Whatever we do, we need to have the range. Here also, my inputs and outputs are a scalar, obviously, right? They can be multidimensional, but that will be more complicated fuzzy inference system. Here, we assume that these are scalar. Okay, where were we? Yeah, so, and again, what about the shape of the membership functions? This is determined by us, the designers of the fuzzy inference system, but we can get hints from the expert, right? So for example, the expert, we can ask the expert, what range can the slope be? When they will say between -10 and 10, then we say, okay, so for negative, you mean somewhere around here, right? And they might say yes, or we might not even ask. We might not even bother asking, and we determine it ourselves. It's our decision. Also, what shape of membership function we should use. Again, this is our decision. Let me tell you, so you might think that everything is our decision, then how do we know what is the best thing? Then in fuzzy inference system, I should tell you that we need a lot of trial and error in application, in practice. I'm saying that in theory, I can give you what membership functions you should use, or it can be determined easily. But in practice, it's not known a priori, right? So what do? You, for example, say, okay, let me use a triangular membership function here, or a bit move it there, and then also for this trapezoidal I use, and for this I use trapezoidal, 3 trapezoidals, or one might say I use Gaussian. And also note that for every variable, you don't have to use the same membership functions for the different values of that. For example, here for a slope, for a 0 slope, I can use triangular, but for positive and negative, I can use trapezoidal. For example, what do I mean? I mean this. This is also a very well-known technique used in fuzzy inference systems, right? So it's your decision. You have a lot of freedom. I agree that when you give a lot of freedom to the user, that's the flaw of algorithm, because according to existential philosophy, we have 4 concerns. So Erwin Yalom has talked about these things. We have one of the existential problems or concerns is death. One of them is loneliness. One of them is freedom and responsibility. The other one is, let me remember. So loneliness, death. Okay, there was a 4th one, which I don't remember right now. Sorry. I can't memorize things very well. I apologize. So, but the thing that I want to talk about is the freedom, because in existential philosophy, they say that whenever humans don't like freedom much, because if you give them freedom, you are also giving them responsibility for that freedom. So that's why you need to do the things in your algorithm as much as you can, and give only few number of hyperparameters to the user. For example, one of the many reasons that deep learning is flourishing these days is that it takes care of a lot of things. So it doesn't matter much. I'm saying that it doesn't matter much what learning rate you use or what batch size you use. Almost all of them work well. So that's why user is comfortable, because the user doesn't want to have responsibility. Anyways, where were we? So I was saying that so these are determined by you, both location of the membership functions and the shapes of the membership functions. But how do you determine them? By trial and error. You do that and see how then you use these in your fuzzy inference system and see how it works. If it is working well, done. If not, you will change either the rules or the membership functions or the locations of membership functions or all. So you have several things: rules, which goes back and forth between you and the expert, rules, the membership functions, shapes, and the membership function values. Also, even by changing the rules, you can change the number of variables, the number of values that every variable can get. For example, what if I change the rules so the slope only has negative and positive, it doesn't have 0? So then this membership function will be eliminated, right? Again, everything is in your hands. But in exam, I will either give you the membership functions, or you will determine them in a way, maybe using I need to think about it, but maybe using the previous slide deck. Anyways, Where were we? So I'm saying that in the exam, I will not give that freedom to you. So you don't need to worry what membership function you need to choose. Okay, anyways, so let's continue. So assume I want to design these and within these membership values. So the first rule, now I'm gonna implement this as a Mamdani fuzzy inference system. If a slope is negative and gear is low, then gas should be low. If a slope is negative, just give me a second. Yes. So assume I'm writing down the yes rules. Okay. Just give me a second. Okay, so it says if a slope is negative, right? So what does it mean? A slope negative is this, -10, 0. So this is negative, right? Sorry, I need to change this part. By the way, I can write these things on top of them. I forgot. So this is negative. This is 0. This is positive. Here is low, high. Gas was low, medium, large, right? So, okay, where were we? So we said if a slope is negative, -10, -5, 0, is 1. And mu slope. If, let me think. So what was the rule? I'm reading the rules. Gear is low. Okay, gear, what is gear? Gear is here, right? Gear low is this. Then gas should be high, right? So gas should be high or large, sorry. Gas should be low. Gas should be low, I apologize. Gas should be low, which is this, between 2 and 4. Sorry. Just give me a second. Okay. Gas should be low. And as you see, these are all in the same thing, same range, right? 1. By the way, please bring ruler to the exam for drawing these things. I think that would be easier for you. And then what do we have? So the next rule, if a slope is negative, slope is yes, slope is negative again. So for the second rule, this part is the same. As you see, I'm trying to align everything. So here aligns here. Also, these parts align each other. So try to align everything in your drawing. What was that? So gear is high, if gear is high. What was gear high? Is between 2 and 5. And then gas should be medium. Gas should be medium. So gas should be between 2 and 8. Okay, let me pause here and draw all of these things, and then I come back to you. Okay, so so I drew these things, and now let me show you how they became. Yes, something like that. So these are the 4 rules that we had, and here we are having that. Here I had made a mistake, I corrected that. By the way, for the alignment, the vertical alignments are important. Horizontal alignments, you don't need to care about it much, but you need to be careful. I will let you know when. But for vertical alignments are important, right? Okay, so these are the rules. As you see, for these 2 rules, I don't have any membership function for gear. All right. Okay, now assume my input comes and I fuzzify it, okay, using any technique that we talked about it here. Let me think about it. So yeah, it can be singleton, it can be these triangular function method, etc., right? So either I give you a crisp signal and I want you to fuzzify it and then use it, or I give you the fuzzified signal. So assume uh, my fuzzified signal is this after fuzzification. Let me think. So yes, minus yes, here, sorry. Assume it is like this, minus 10, minus 5. It can be, right? It can be a fuzzified input signal or a slope, I mean, right? So mu slope prime x, right? X. And assume for my gear, by the way, of course, the domain of the slope prime should be the same as the domain of slope, right? So between minus 10 and 10. And the domain of gear prime should be the same as the domain of gear, which is between 0 and 5. So assume, let me think. Yes. So yes, let's make it between 2 and 3. Assume my fuzzified gear, which is gear prime, I mean, is this. Or it can be a singleton method, a singleton. We can have used a singleton methods too, right? For example, this can be also a membership function. Anyways, for here, I'm assuming that it is This is the fuzzified. I'm saying that if we use singleton, maybe this could be the fuzzy input. Anyways, now what are we gonna do? You tell me. So here, so I'm having, do you remember this? Here. So I'm having them here as input. I'm just repeating this here. And for gear, it was between 2 and, let it be between 2 and 3. I think that would be easier. 2 and 3. Okay, now what do we do? Let's put them one by one in the rules. So, sorry. Maybe we can, yeah, we should do it by dash lines. Right? I'm just repeating. I'm just repeating this here in the dash line in all of the rules. That's where I was talking about. You should be careful. So I didn't align them vertically. So I only considered the horizontal alignment. Horizontal alignment is important. Although the vertical alignment, I ignored that, but I was careful that it's between -10 and -5. Here also put it between -10 and -5. Here also I put it between -10 and -5. So you need to be careful. I should, for example, if I had put it here, that would be wrong, right? Because it's between -10 and -5. Also, that would be here, between -10 and -5, right? Okay, now you told me for gear, yeah, for gear, so I put them here too again. Right? Now we need to do you remember? So what were we doing here in Mamdani? So we said that what is the T norm between mu A1 and mu A prime? Likewise here, what is the T norm between mu slope and mu slope prime? It's this, right? Also here, it's this. Also here, it's just this point. Here, it's nothing, right? Zero. What about T norm between gear and gear prime? It's here, and also it's here. And for these two, we don't have any gear prime, right? So now, okay, now I need to calculate, because this gives me one of the W's, right? And also this gives me one of the W's. Do you agree? So they come, if you don't remember, recall this slide. So now I need to get these as well as these, then their T norm, right? Which gives me this. This is W1 for the rule 1, right? What about this one? It gives you this. Also, it gives you this, if I can draw them well. It gives you W2. We need to calculate which one is higher, which one is lower. I'm not sure, okay? But for this one, at least it's obvious that this one is lower and this is the result of T norm. For this one, it gives us only 0, and the other one, there is no other thing. So we don't need to even calculate T norm. So it's W3. If we had something else, then we need to, for gear in the rule, then we had to do T norm again for them. So here also 0, W4. It could be more than 0, but here by chance it became 0. Okay, anyways, so now you told me. So here, I want to calculate this. So for this one, I don't need to calculate this because the T norm, for T norm, the result is this. So I don't need to calculate this. What is this? Then I need to find the intersection of these two lines. Okay, let's see. Let me write it. Between -10 and -5. Right, and this is 1. Okay, you tell me. What is the equation of this line? So let me think. Let's call it y and x, doesn't matter. So y and x. Let me think. So y minus 1 slope times x plus 5, right? I'm just writing the equation of the line. And what is the slope? 1 minus -10. No, sorry. I apologize. Y minus 1 minus 0 minus 5 minus -10. Yes. So it is 1 y minus 1, 1, 10 minus 5 is 5, x plus 5, in other words, is x over 5 plus 1. So y equals x. So this is the equation of this line. Am I right? So let's check it. If x is 0, no, if y is 0, then x is -10. Correct. Then what about this line? The equation of this line. So y minus 0 equals the slope times x minus -5. What is the slope? 0 minus 1. 0 minus 1, yes. -5 minus -10. So it will be y equals -1. Yes. Minus x over 5 minus 1. So y equals -x over 5 minus 1. Now we need to intersect these two lines to find this point, right? So if I intersect them, this one and this one, then x over 5 plus 2 equals -x over 5 minus 1. Then 2x over 5 equals minus 3. Yes, x equals minus 15 over 2. Then y becomes minus 15 over 2 times 5. Let me write it better. So I'm using this now. Minus 15 over 2 times 5 plus 2. So they cancel each other. Minus 3 over 2 plus 2. So 2 minus 3 plus 4. Half. So this is half. This becomes half. As a result, this is half. Right? Half and 1, their T norm becomes half. What about these two? We need to calculate. I'm not sure which one is the smaller. Okay, let's calculate it. So this one is half. We already calculated that because it's very similar to this. It's exactly the same as this, right? But what about this one? So it's between 2, 3, 4, 5. Sorry, my device sometimes gets disconnected. Okay, where were we? So 2, 3, 4, 5. Yes. And 2, 3. Okay, let me think. So what is the equation of this line? Let's calculate. Y minus 0 equals the slope time x minus 2. What is the slope? 1 minus 0, 3 minus 2. So y equals x minus 2, right? What is the equation of this line? Equals 3, right? Now intersection of these two becomes y equals 3 minus 2 equals 1. Uh, let me think if I made any mistake. Yeah, sorry. So that was my bad drawing. See, here I found out that that was my bad drawing. That was my bad drawing. Even if you make some mistakes in your drawing, that's why I asked you to bring rulers. If you make mistakes, then by calculation, you might find out that you made a mistake in drawing. So that was 1. I just calculated that, and that was 1, and that was half. Again, this gives me half, right? So that was my bad drawing. In other words, what I drew here was this. That was a good example of bad drawing. So yeah, and I just found out. Anyways, so we calculated the firing strengths of rule 1, rule 2, rule 3, rule 4, all of them. For rule 3 and rule 4, by chance it became easy, but it can be a bit more complicated. Anyways, then what do we do? You tell me. So now, again, I know that this is half. As a result, this is half. So as my I didn't draw them very very carefully. I didn't align them very, horizontally carefully. So I need to do this because this is half, right? Then what happens according to this slide? We need to get the T norm, right? So the T norm. For why it is T norm, we already have proved these things, all of these in the previous session, in the main lecture. I'm just here I'm solving some example. And also here, half, it gives me this. 0 gives me this, nothing. 0 also gives me nothing, right? Now, recall this slide. I need to have the S norm between them. So what did we find? Let me, if I can, copy and paste these parts so I don't draw them again. Now, what is the S norm of all of them? Let's put them all together. So 0, 2, 4, 6, 8, 10. What is this one? It's this one, of course, we need to calculate this point, this intersection point. We will do that. For now, let's just draw it. So basically it would be like this, right? Let me try to draw it well. Okay, that was one thing. So now I need to erase this part. Okay, so that was the first one. Now the second one. The second output is between this. I guess it will be like this, but of course, I will verify it by calculating the intersections. We will verify it, right? And for the other ones, it's 0 and 0, right? So let's calculate these intersections to make sure whether we drew this correctly or not. So what is you tell me, what is the equation of this line? Let me think. Y minus 0 equals the slope times x minus 4. And just 0 minus 1, 4 minus 2. And this line, its equation is y equals half, right? So intersection of these two, this line was again my device. So what were I saying? So this line is y equals half, and this one line is this. We intersect them. X equals, no, obviously I made a mistake. Let me think. Let me think, because x definitely needs to be between 2 and 4, and I think it will be 3. Just give me a second to double check my calculations. Oh, yes, here I made a mistake. Um, 2. So it's 2 here. Here it's also 2. And here I will get 3. Right? So this will be 3, this intersection. Here it is 3. What about these two? Let's calculate them very fast. We don't have much time. Y minus 0. The other, and also we have y equals half. Intersection of them is x equals 3. So this is also 3. That's why our drawing was correct. And this, for both this and this is 3, right? Otherwise, we would correct our drawing. If you use ruler, I think that would be easier for you to find it out. And what about this one? Just give me a second. Y minus, so the equation of the line, y minus 0 equals x minus 8. and y equals half, their intersection becomes just give me a second. I can do this too. Yes, x equals 7. So that would be 7. So so here I drew it incorrectly. I need to correct that part. This is 7. Okay. Now let me copy this part. Okay, we have this. In other words, aggregate S norm becomes its S norm becomes this, right? The whole thing together. Right? So what was that? It was the output. Mu gas prime, whatever we call it. What did we call it in the slides? Mu C, mu gas set. Anyway. So now this is the fuzzy output, right? We need to defuzzify it. It depends on what defuzzification methods we use. Let's practice several of them, several defuzzification methods. So, for example, we can use centroid method. The simplest one are these. So let me think. Here, mean of maximum might not be very useful. Why? Because we have here, if you see my cursor here, it's almost all of them is our maximum. We don't have a bunch of discrete modes. And mean of maxima is usually useful when we have a bunch of discrete modes. So usually when we have continuous membership function. Let me think. What about largest of maximum or smallest of maximum? You tell me. So the largest of maximum says it is 7. So the defuzzified will be 7, right? So the maximum is in this range, and the largest is 7. Smallest of maximum is 0 here in this case, right? What about the rest? So threshold method, assume, yeah, we can also have threshold method if you remember, prior to any other defuzzification method, right? So it's a meta algorithm for defuzzification, and it can be used along with any other defuzzification algorithm. What about bisector and centroid method? So both centroid method and bisector of area need integral. We need to calculate integral. Let's do it as it is here in our case. The function, the membership function, is piecewise linear. Calculation of integral is very easy. So what is centroid method? For that, we need to calculate for integral of x mu x dx, right, on the support set. So let's do this. Let's do this. I'm calculating it here for centroid method. So integral. So what is the support here? It's between 0 and 8, right? So 8 until 10, for example, is not in the support set anymore because the membership value is 0. Here, it's between 0 and 8, x mu gas of x dx. Okay, now you tell me. Of course, we need to break it down into these two parts, into the pieces of linear functions. So 0 until 7, x half dx plus 7 until 8, x. What is the equation of this line? Let's calculate it. Y minus 0, x minus 8, right? Yes. Be careful that this is half, not 1, right? So okay, so its equation is, I think it doesn't fit. I need to come to the new line. Plus 7 to 8 x minus x over 2 plus 4 dx. Okay, what is the first integral? 1 over 2 is a constant, comes out of the integral. So let me calculate this. Here, because of lack of space, I'm writing it in a busy way, but in exam sheets, please write it in a clean way, okay? But for here, just accept my excuse, and I'm writing it a bit in a busy way. Anyways, it will be x squared over 2, right? This integral. X squared over 2 plus c, the constant, but we don't care about the constant because it goes away as we have the range for the integral. So between 0 and 7, what would it be? Let me continue it here. So it will be 1 over 4 x squared. So 7 squared minus 0 squared. 49 over 4, right? Now let's calculate this integral. So this has two parts, minus x over x squared over 2 plus 4x. So it becomes minus half x cubed over 3 plus 4x squared over 2. Again, the constants go away. 7 to 8. So it becomes 1 minus 1 over 6. We need to calculate this. Let me calculate it. So so it becomes minus 2816 plus 30. So in other words, 30 minus 28.16. Yes, so what about this one? 12.25. Okay, now I need to add them together, right? For the centroid method. Or that to calculate, because I need this, right? So then mu x Yes, mu x dx becomes 12.25 over plus 1.84. Now in the denominator of this formula, we have just the integral of mu x, right? By the way, we don't use summation because here we are continuous membership function. We use integral. So also we need to calculate mu x dx. Am I right? Yes. So what will it be? It will be a bit different. This time it will be integral of, just give me a second, half dx 0 to 7 and 7 to 8. It will be minus x over 2 plus 4. So it will be 1 over 2x plus minus half x squared over 2 and plus 4x between 7 and 8. Okay, by the way, by this I mean the range. It's not the integral sign. Okay, so now it will be, I think calculation of integral is easy for you, right? So I'm just practicing it here for you. So it will be half over 7 over 2. Let me calculate. Okay. So now the total formula, equation 4, c hat, or whatever we call it, c hat, is, what was that? Oh, I didn't sum them up, I guess. So it will be 14.09 over 3.75. It will be 3.757. Does it make sense? Let's see. First off, your defuzzified value has to be in the first in the domain of the output. So here the domain is between 0 and 10. Is it? Yes. Also, usually, as far as I can think of, it has to be in the support set. Otherwise, it doesn't make sense that, for example, we find 9 as a defuzzified value because it's outside of the support set. So it needs to be between 0 and 8. Is it? Yes. And now let's see visually. We found 3.75, something like that. Yes, centroid method almost is kind of in the middle. So that's correct. We just found this, we defuzzified by centroid method. What about bisector method? Bisector, we need to solve this equation 10 for c hat, right? Let's do that. Let me copy this membership function. So what does it say? So let's write it down. Write this formula down. Let me write it down. Minimum. I'm just writing down this formula in my sheet. Okay, what is mean? Support set is here between 0 and 8. So mean of support set is 0 and maximum support set is 8, right? By the way, here our value variable is scalar. Otherwise, we will have multiple integrals. So this is a single integral, right? Anyways, so 0 to c hat mu x. What is mu x? So, okay, I will talk about it to you. Equals c hat to 8 mu x dx. Okay, then, so the mu x has several parts, right? Mu x has several parts. This part and this part. Let's break it down. 0 to 7. No. Okay. I think for this, as far as I remember, we need to guess where the c hat will be. So what is bisector doing? It's basically saying that I want the area before the area of behind the area under the membership function. Before c hat be equal to the area below the membership function after c hat, right? So basically it should be in the middle. So I guess in this case, my c hat will be less than 7, obviously. So as a result, I can simplify it to 0 c hat, and my mu x, maybe here, around here. So my mu x is half. Okay, for this one, then I need to break it down. Until 7 is half, and 7 to 8, it's this line. What was the equation of this line? We already calculated that here. Minus x over 2 plus 4. Okay, let's solve this. Then what happens? This becomes 1 over 2 x. This becomes half x again. This becomes okay. Now what happens? Okay, now we need to say c hat here minus 0 is then this part. 7 minus c hat plus I think once I calculated this, it's minus 3.75. And this is 4. Okay, so basically it becomes c hat over 2 equals 7 over 2 or 3.5 minus c hat over 2 minus 3.75 plus 4. Let's calculate this. 3.75, okay? So basically it becomes 3.75 minus c hat over 2. As a result, c hat, so I bring this to the other side, c hat becomes 3.75. Does it make sense? Is it in the domain of output? Yes, between 0 and 10. Is it in the support set? Yes, between 0 and 8. Is it kind of in the middle? because it needs to separate the area into two equal areas, right? Yes, almost equal. And here, interestingly, it's not a completely, of course, it's by chance, the solution of bisector and centroid method might be the same, but here they are different. Usually they are different, right? 3.75 for centroid. For bisector method, it becomes no, by chance. I think by chance this one it became equal. Sorry, but sometimes it is different. So they don't have to be equal to each other. Anyways, so I solved some defuzzification for you too, and now what if we wanna do Sugeno or Tsukamoto? Then what happens? Can I copy the whole thing here? Just let me. I need to copy this because it's very big. I don't know how to copy the whole thing. It's very big. I can't copy. Just anyways, just let me pause it here. Okay, so for Sugeno, kind of this, I couldn't copy the fuzzified signals here because it was too big. Anyways, and this was Sugeno, right? So now we can do what? We can say this is Z1, Z2. So we can have some functions for the rules. Again, we can get these functions either ourselves or from the experts, right? As soon I do this and I get these functions from the experts, so I don't have these parts in Sugeno. Then what happened? Then I will have so assume, I don't know what do we call it, my gas, let's call it G equals we can say 3 slope plus 2 gear, maybe. Or here for this, I can say 3 gas squared only. Anyways, so I can define these to be, usually we use polynomial functions. Here I can use gear plus 5. Here I can use gear equals 1. So then what happens? Then we have, so for this we need, for Sugeno, we need the inputs before fuzzification as well. So before fuzzification, assume my S was what? Do you remember? My fuzzified S was like this, right? So maybe my crisp slope was minus 10. So its fuzzified membership function was like this. Anyways, also my fuzzified gear was this. Maybe its crisp was 2.5. So now, as a result, G1 becomes, so this is G1, G2, G3. Sorry, my device is not working right now. So I was saying, by the way, I noticed that gas and gear both start with G. Let's call gas with, I don't know, F. Okay. So maybe F1, F2, F3, F4. As a result, F1 becomes, maybe internet is unstable here, I don't know. So F1 becomes 3 minus plus 2 G. F2 becomes 3 minus 10 squared. F3 becomes G plus 5, 2.5 plus 5. F4 becomes 1. So let's calculate these. Minus 30 plus 5, it becomes minus 25. F2. By the way, I'm assuming that my gas, which is F, here in my Sugeno, I can determine the functions in a way that the board of the function, or the range of the function, output range of the function becomes, what was the range of the output? But I can, um, hello? Yes, sorry, I think internet in campus is not very stable right now. I don't know what to do about it. Anyways, uh, so if my device can work properly, it's not working. Okay, apologies for disconnections. But anyways, let me repeat what I was saying. So I was saying that here, uh, I can choose my functions in a way that the range or output range of the function for gas becomes between 0 and 10 as expected. But here, I'm assuming that it's not between 0 and 10. Okay, I switched to my phone data. Anyways, whatever. So I've seen that uh, these functions here, the range might go beyond the acceptable range, but I can tune these functions in a way that they become between 0 and 10. Anyways, for now, assume that's okay to have my minus 25. Then this becomes 300. This becomes 7.5. This is 1, right? Now, how do we combine these? I think, yeah. So then we need to use these W's, right? In other words, my final F is W1 F1 plus W2 F2 plus W3 F3 plus W4 F4 over F1 plus F2 plus, no, just give me a second, over, sorry, over W1 plus W2 plus W3 plus W4. Yes, because what are we doing here? Basically, we are dividing every weight by the summation of weights. So the weights become between 0 and 1 and they sum to 1. And here, then what happens? W3 and 4 are 0. So they go away here in our case. Then W1 and W2 are both half. So it becomes half F1 plus half F2 half plus half. In other words, it's F1 plus F2, which is minus 25 and 300. So that was for Sugeno. What about for Tsukamoto? So here, assuming that so here for Tsukamoto, our membership functions for the output need to be monotonic. Assume this is a monotonic function. Let me think. Assume, I don't know. It is like this, a line. And also assume it's like a line or a curve. If in exam, if I give you to Tsukamoto, I will give you a line so you can calculate the intersection easily, right? Or the inverse easily. So here, for example, we do this and then we find the inverse. How do we find the inverse in this case? Let me solve one example for you and the rest I will leave it to you. So for example, for this one, I want to calculate the inverse. So what is the equation of this line? It's y minus 1 right? What is the equation of this line? So basically its inverse is 2. As a result, the crisp output of rule 1 into Tsukamoto becomes 2 for this case, right? Then we do this for the other one, 2, the other one, 2, and the other one. And then we again combine them using similar weighted average here. Yeah, I think already solved enough questions for you, and now I think you know what you should study and how you should study. This was for fuzzy inference system. For fuzzy logic and fuzzy sets, I think that's also easy and straightforward. The operations are easy. I hope it was useful for you. Thank you very much. Bye.